Meyer, J.P. Clark, and Paul Aramenko for being our distinguished speakers. We're seeing a lot of action come out of these meetings, and we're really excited to keep that momentum going. So good work, everybody. We definitely want to thank the Vertical Flight Society for providing us this network and platform to do these types of councils. That's just one of the benefits for being a member of the Vertical Flight Society. So we request that you guys all become a member if you're not already. There are other meetings like this, like the Flight Test Committee or Council, among numerous technical documents. And, even if you're not interested in the technical aspect of it, oftentimes after these calls, we'll get asked to introduce some of you folks to each other. So I just want to point out that if you join the Vertical Flight Society, you can contact members directly through the hover.org. It's sort of like the social media within Vertical Flight Society. So just one of the many, many benefits of becoming a Vertical Flight Society member. So again,
just a quick clarification on that. That's hover.vtol.org.
Thank you. I don't know what I said, but thanks, Mike. Yeah, so just requesting everybody become a member. And yeah. So thanks. And Anna Bob wanted to say thanks for being a key organizer. And I'll try to do my best to put it in your words, but feel free to jump in and say something if you want. But the mission of this council is simple. We want to find out how to make hydrogen a reality in eVTOL. And that's it. And the starting point is to find out, what's available, what's now on the ground. And so that's why the council we're putting together this plan for fact finding so we can eventually lay out a blueprint for the future. Anna Bob, do you want to add anything to that?
No, that's excellent. We all know the infrastructure bill is the movement towards that is coming up. So we want to find out what needs to happen at the higher U.S. government level intelligently. So
good point. We definitely need to be on that. We are still looking for a contact at Hydrogen Forward. I believe we have somebody from Shell that was going to introduce us. So if that person is on this call, just a friendly reminder to introduce us to somebody over there. Okay, good.
Yeah, hi,
David.
It's David Leitner from Shell. I have an action with one of our contacts, Arnab. He's our SME in that space, and I have reached out to him. He's gone through the happy phase of having a child added to his family. So he's away on paternity leave at the moment, but I'll keep chasing him. And hopefully within the next week or two, we'll have some success.
Perfect. Thanks so much, David. Thanks for that update. And congratulations to him and his family. So we are all very excited. I know I am about HyPoint and technology behind these amazing numbers that, will pretty much be a game changer for all of us here. Brian Benicewicz, and I hope I'm saying your name correctly. He's the director of science at HyPoint. He's the inventor of the high temperature membrane, and he holds over 50 patents. So without further ado, please welcome Brian to the stage.
Thank you, Danielle, first off for the invitation to talk to everyone today, and also for the introduction. I'm going to share my screen. Can you all see that?
Can you maximize that?
Yeah.
Go on presentation mode, I think it is.
Is that it?
Yeah, that's fine for now.
It was on mine anyway.
Yeah.
It's very small, like you're in if you have it on two screens, maybe. Are you using two screens?
I see just one big one in front of me.
Yeah, it's coming through very small.
Do you see a button that says switch screens or swap screens?
Well, let me try this again. here's the full screen is slideshow.
Right.
Well, you could probably use that. Yeah, go
Yeah.
back to what you just had.
Go back one.
Yeah, that would be better actually.
Yeah,
to
go back, and then you can actually pull one of the bars over to minimize the slide.
Yeah.
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 And you can
Is that better?
lengthen the box a little bit too.
Or
And
you
then-
can, yeah,
Yeah.
you could
Yeah.
minimize the ribbon at the top.
Let's see. Whoops. Can't go too much. Like,
That's
do I get
pretty
rid of
good. That's
Do
pretty
you know
good.
how to hide the menus at the top?
no, usually I do just the full screen and that gets rid of it.
Yeah, double
If
click on where it says,
if you click home again, where it says home, click that part. It will eliminate the
yeah, if you
it will
double
eliminate the
click.
ribbon
Right.
all the way to the left, where it says home.
I don't, wait a minute, let me see. Home.
Sorry, no, in the menu. So double,
In the menu on the top. No. Next line in one of those where it said home, insert, draw, design.
Word home with the red underline. That's it.
Click that.
There you go.
There you go.
Yeah.
Click one
Yeah,
time.
perfect.
Okay.
Is that all right up with him?
Yeah.
Okay.
Continuing education credits.
Yeah, thanks. Nobody's got their microphone on because I'm hearing a lot of background. Thank you. So again, thanks for the invitation and introduction. Today, Danielle asked me to give maybe a little background on just what a hydrogen fuel cell is. And so I'll briefly describe hydrogen fuel cells and some different types and applications. But we're also going to tell you a lot about what HyPoint is doing in this space, because we're doing I think some very interesting things. I'll start by giving you a little more detailed background of just what I've done over the last few years. Got my PhD in polymer chemistry, because that's the development of the high temp membrane in a few years ago at University of Connecticut. Went straight into industry and worked in the chemical industry and also biomaterials industry with J&J. And then in '85, I went to Los Alamos National Laboratory, was a scientist, and then I went to a couple of management levels, a section leader and deputy group leader of a large material science development group. In '97, I left and I went to Rensselaer Polytechnic Institute, where I was chemistry professor and also director of the New York State Center for Polymer Synthesis. And then in 2008, I went into my present position, which is a chemistry professor again, and I'm also holder of the Smart State Endowed Chair in Polymer and Nanocomposites. And then along the way, I co-founded a couple of companies related to hydrogen H2 Pump LLC, as well as, of course, co-founded HyPoint, where I'm head of the science efforts and also now serving as one of the board of directors. And so we have a very powerful team. It's headed up by Alex Sabanenko, who has Ph.D. in electrochemistry and then built his career in international business over the last many years in U.S. corporations. He has a lot of experience in taking projects from R&D stages to full commercialization. He is assisted by another, my co-founder, Sergey Shemenkov, who's the vice president of R&D. Sergey has more than 15 years of development work in hydrogen fuel cells and was trained, got his PhD in physics with Ginsberg, famously Nobel Prize winner. And also on our team, we have Rhonda Stout, who's our chief engineer. Rhonda has a huge amount of experience that she gained at Plug Power for many years and is our expert in everything from the membrane, electrode assembly, all the way up through stacks and systems and manufacturing. We are also assisted by some key advisors, Ken Gurchi, Arvid Nasro, John Hamilton, Val Miftakov. All of these folks have many decades of experience in high technologies, aviation, fuel cells, and of course, bringing things to market. So we're always grateful for their guidance and advice. And so with this overall team, we're ready to address almost any of the challenges and risk as we move fuel cells into the air transportation market. We're not strangers. This is supposed to be a movie, but if I'm not in presenter mode, I guess that's not going to work, but that's okay. We're not strangers to hydrogen fuel cell technologies. Previous versions of the company have validated key parts of our technology by developing best-in-class fuel cells for drones and robots. And we've already built and sold solutions for real business applications. In fact, this earlier development work has allowed us to get a lot of the necessary technologies as well as knowledge to develop the next generation fuel cells, which are needed for air transportation, which is the interest of everyone here. Unfortunately, this was supposed to come up in stages so I could walk you through it, but that's okay. I'll walk you through it anyway. So we have a problem. And that problem is really that the arrival of zero emission aviation vehicles has been limited by the energy density limitation of lithium ion batteries. So it takes around 500 watt hours per kilogram roughly to fly a plane 600 miles. And current lithium ion batteries can deliver maybe about 200. And this extra power is needed because, of course, in air transportation, you have to get your vehicle off the ground. And so we don't see any pathway here to take lithium ion batteries to really satisfy the market. At the same time, current fuel cells can deliver the energy density needed for power air vehicles, but fall short. And we think probably you need at least 1,500 watts per kilogram in order for satisfy the market for air transportation. But current fuel cells can maybe get to 600. And so what we've done is really solve some of these issues by building the next generation fuel cell, which is based on our architecture of this turbo air-cooled system. And we have recently demonstrated, and I'll elaborate a little bit today, that we now are able to reach 2,000 watts or 2 kilowatts per kilogram and 1,000 watt hours per kilogram in our systems. And this is really what aircraft designers are looking for. Let me tell you a little bit also about our product development recently. So in December, just a few months ago, we built a fully operational prototype, which was a very important step in our development because there were a lot of technological and fundamental validations that were concentrated into the single prototype. And this was based on high temperature PEM membranes. And so this was very important for us. We finished our testing program, and the data we got from this testing program really confirmed that we could achieve greater than the 2 kilowatt per kilogram at a system level. And so based on our agreement with customers, and after this successful prototype development, we're ready to build a full-scale system which should be delivered to a customer in 2022 for a flight test. And scaling from the short stack through a 15 kilowatt intermediate module to the eventual full system is really not, in our mind, a fundamental modifications. It's really just the same system, but in a larger form factor. And what it does really is require a more accurate execution of our engineering work. If there's a few people who don't know how a fuel cell works, so let me just throw in the most basic diagram I can imagine. Hydrogen is a really simple molecule, even if you're not a chemist, and it's really composed of 2 protons and 2 electrons. So what we do is we're going to rip this apart using a catalyst. We're going to move the electrons through an outer circuit and the protons through some kind of a membrane. And then we're going to recombine the electrons, the protons. We're going to borrow some oxygen from air and make water. And of course, what we really want to do is move the electrons through this outer circuit so we can do some useful work, light a light bulb, maybe run a laptop, a car, or in our case, we really want to generate enough power to support air transportation. And so it does require an awful lot from this membrane, but the technologies are here today, we believe, to do that. So that's the simplest diagram I can imagine for how a fuel cell works. Fuel cells are not new. Originally invented, William Grove did in 1839, and frankly, not much happened for about 100 years. Francis Bacon is given credit for reinventing the fuel cell, if you will, or rediscovering. But even then, it was kind of an industrial curiosity for a while. I think it got a lot of notoriety once we hit the 1960s because it was used in the space program. And then I think from about roughly the 1990s on, we see what you could call the entrepreneurial phase and really birth of a new industry of bringing fuel cells to a variety of markets, which we continue to do today. There's many different types of fuel cells. I'm just going to briefly touch on each of the types and give you a little bit of the pros and cons, particularly from the viewpoint of use in aviation. And I'll end up with the high temp PEM because that's the one we think is going to really solve the problems. Again, I mentioned alkaline fuel cells have been around for a while. They were used in Apollo space missions. The picture here is in fact one of those that delivered between 600 and 1400 watts for these space missions. It operates just under 100 degrees C most of the time. The electrolyte, which is used to move the protons across that membrane, is potassium hydroxide. This is very corrosive material. So the pros are you've got reasonably high performance, fairly simple design. And the cons were this is pretty high weight for this power. And unfortunately, this electrolyte is poisoned by CO2. So for this to operate, you have to have some subsystems to make sure carbon dioxide from the atmosphere doesn't get into the cell. And so pretty much limited to space and military type applications. Solid oxide fuel cells have gotten some attention recently. Its temperature of operation is pretty high, 800 to 1,000 degrees C roughly. It uses a solid thin oxide film to move the protons. So the pros here, it's pretty high efficiency. Flexibility of fuel types. You can use hydrogen. You can take some more complex fuels, some hydrocarbons, and reform them and pull that hydrogen out to make them operate. But the cons are obviously this high temperature enhances the corrosion and breakdown of cell components. You have much longer startup and shutdown cycles, and that can also create some thermal fatigue and cracking of the various parts. Used mostly for electric utility. So here's a famous picture that shows several of these solid oxide fuel cell installations, and they were having a little ceremony for kickoff of those, but very good for electrical utility applications. Another one that's been around for quite some time is the molten carbonate fuel cells. So these are made at the megawatt power levels, so that certainly can be done, and shows you an installation that has several of these. It uses a carbonate kind of salt to move the protons. Again, these are high efficiency, flexible in fuel cell and fuel types. You can do internal reforming easily, and then it's more tolerant to carbon monoxide CO and carbon dioxide CO2. The cons are, of course, the same as the previous one for all these high temperature operations, and that it enhances corrosion and breakdown of the cell components, much longer startup and shutdown cycles to go from room temperature all the way up to operating. And it creates thermal fatigue as you do this and cracking of the parts. And again, as you see in the picture here, it's very good for electric utility applications. Low temp PEMs have also been very much in the news. This is a photograph of the Toyota Mirai fuel cell engine. And this operates at much lower temperatures, roughly between 60 and 100 C. It uses a polymer membrane that's got a lot of water in it. It's a well-developed technology. That's one of the things going for it quite a bit. And it's got quick startup time because you don't have to get quite as hot. But it's very sensitive to fuel impurities. And it's not so much the polymer membrane, but the catalyst at these temperatures is poisoned by small amounts of carbon monoxide. So one has to be careful of that. and it's very sensitive to the amount of water that's in the membrane. And so there's a lot of work done over the last 2 decades on trying to handle and manage these water issues, which is difficult because people like to push it closer to the 100-degree operating temperature, which now you're approaching the boiling point of water. So you don't want to evaporate all that off. So it's a little bit of a trickier water management issue there. But it has found applications in utility, electric utility, portable power, and what you might call terrestrial transportation, AKA cars and trucks. And so that's the kind of current state of the art. Well, we're very interested in the high temperature PEM fuel cells. The temperature operational range now is between 120 and 200 degrees C. And the electrolyte is a different polymer membrane that has phosphoric acid in it, which does not evaporate at 100 degrees C. So the pros are still fairly low temperature and fairly quick startup times. Again, the simple design is a good thing. And at these temperatures, that catalyst is way more tolerant to fuel impurities than it is below 100. And since we don't rely on water, we don't really have all those water management issues and the balance of plant that goes along with that. It's very scalable in its design and importantly can be air cooled. And the polymer chemistry is a little bit cheaper also. The cons are, well, we're probably only about 50% of what we can get out of this so far, which is maybe good news because we have lots of room to improve. And there's maybe just a handful of manufacturers of the key membrane. And we have seen already applications in portable, stationary, transportation, terrestrial, and we're going to show you that it's also very good for, and excellent actually, for aviation because you can achieve both high specific power and the energy density. So if we look at the whole landscape here, our path to aviation is maybe on a diagram like this. We have the solid oxide and molten carbonates are good for the stationary applications, but don't have very high specific power needed for aviation. The alkaline, I guess you could put it where it's got some air transportation applications since has been used in Apollo missions, but it still is fairly low in specific power. A lot of the attention has been done to low temp PEMs. And so you can see it's useful for stationary, terrestrial, and even of our own work has shown this in drones and type applications. The high temp PEM was used mostly, at least previously, in stationary and terrestrial applications, but we're going to show you that now with some changes in the architecture of the cell, we can now get this to have some very attractive properties for air transportation because we can increase specific power and a couple of other things that we've done. So I think there was one missing from this somehow, or maybe I skipped it. But anyway, so let me stop there. I really appreciate your attention and the invitation to tell you a little bit about what we've done. And I'll be happy to answer questions and enter into any discussions people might want to enter into. Thank you.
I have a question, Danielle, if no one else.
Go ahead.
Hi, Brian.
Hi.
It's great. Thank you for doing this. Can you explain a little bit in layman's terms what exactly fundamentally is behind making it lighter? Does the IV curve change, or is it because you don't have to chill the air before it's coming in, or less heating requirements?
There's a couple important things. If you look at it from a system level, the balance of plant, particularly when you look at the low temp PEM membranes, it's almost necessary for them to be water cooled. And frankly, water is heavy. And so what we've done is by using a turbo compressor, we are now going to make that do two things for us. One is to go to air cooled without that extra balance of plant from water-based systems, water cooling systems. And secondly, we also now use that turbo compressor to increase the pressure of operation, which does in fact boost the IV curves. substantially. So we actually get two major benefits in this architecture that we're adopting. Does that cover what you were asking?
Yes.
Okay.
Thank you.
Sure.
If I can do a follow-on.
Yeah.
So the automobile people, I'm not very sure, but I think they talk about operating at 2.5 atmosphere or whereabouts. Are you envisioning the same kind of pressure, or is this even higher?
Yeah, no, those are easy pressures to build around without going higher. And yet, even over those modest increases in pressure, there's a substantial boost in the IV curves. And so that's enough for both the flows we need for cooling, as well as for getting higher powers. Mm-hmm.
Thank you.
About the same numbers.
Brian, this is Rory. Thank you for the presentation. I have, I guess, two questions, if I may.
Mm-hmm.
The first one I would put in the theme of certification, on wing, and what you see as the major hurdles on that. And then the second one I would push in the theme of profitability for a company, and in my mind, that for eVTOL space would be, turnaround time, cycles per hour kind of concepts, efficiency, in other words, to get a platform back into the air. So any of those specific refueling gotchas, or once it's implemented on a mass scale. Could you talk to that a little bit, please?
A little bit. Certainly the certification is maybe not exactly in our expertise, but we are working with customers who have far more experience than us in certifying aircraft through all the stages that you need to do. And we plan to work with them to help us, to give them whatever they need to do that. The other side of that question, there's some infrastructure that obviously has to be developed with hydrogen. And the good news is that there's a lot of people putting that in. And so we'll try to work both sides of this equation with along the entire hydrogen value chain to help people know what's required for the hydrogen fueling and things like that, as well as to work with customers who are trying to get to certification. So we're in the middle of probably that whole value chain. Not all of it's going to be us doing it, but we're going to work with everybody to help them get it done. It's not a very specific answer, but that's kind of the reality of how we have to work.
No, I understand. It would be helpful maybe, I realize when you spoke specifically to certification, and yes, I can see why you'll have customers help you go through that process. Can you talk about potentially a little bit, let's say, the failure modes of this kind of fuel system? So not saying that it does have failure modes, but if I think of a failure mode of a conventional fuel system, you pick any one of the kind of jet fuels, the way it's operated inside an aircraft, it's atomized, and that creates, during accidents, rather large and catastrophic like explosions. I'm sure that will be a question for the failure modes during the certification process. I don't know, other than hydrogen being very explosive, what the kind of failure modes are typical for this kind of system. Over.
Sure, we're actually in process of identifying many of them now with a couple of key customers. And so, that's kind of ongoing. It might be a little premature to get into too much. But you're absolutely right. That is what we have to do.
Let me add, colleagues, Brian, if you don't mind, I would add a couple of comments. Rory, thank you for your question. You see, we are. I am head of R&D of HyPoint. My name is Sergey. You see, we follow we follow modular principle in developing our system, and this allows us to dramatically increase reliability of the system from one point of view. So power unit generating electricity divided on a number of independent fuel cell modules allow us to be pretty reliable. From the other side, we believe in hydrogen. You see gaseous hydrogen, compressed hydrogen, also divided by a number of cylinders, not too much dangerous actually. It's how to say, it's not too much reason to be afraid with some explosion with this technology with compressed hydrogen, because this technology is proven many times and certified and could be used actually on board for aircraft platforms.
Yeah, in that
No,
regard.
thank you, Sergey. Yeah,
Yeah.
I mean, I agree. Obviously, it goes into some of the most extreme environments. I mean, it's used in spacecraft that have, you know, the most extreme environment changes. At the same time, maybe what I'll say is a little bit of a catch-22 or chicken and the egg. I know that certification authorities are looking to do things differently. At the same time, I think when new technology comes along, the natural human tendency is to default to, well, how did we certify certain technologies in the old method? And I'm always looking for ways to communicate to certification authorities how to approach the problem differently.
So a good primer on hydrogen safety that we would have access to, Danielle, would be, I see Charlie Myers in the participant list. Charlie provided the FAA Technical Center about a month ago a hydrogen safety overview, and it's widely attended by many people in the FAA, and I think it would be a valuable addition to the agenda for one of our H2 Council meetings. It's a very impressive story about both the history and the current standards for hydrogen safety that create a very compelling positive view with appropriate cautions.
Thank you very much. But I would like to add that we also consider a number of options for hydrogen, including liquid hydrogen, liquefied hydrogen, and some fuels that can be used on board to produce hydrogen on board. So for example, methanol or ammonia could be used in liquid form in order to produce hydrogen on board. So there are a number of options, and our fuel cell, HTPM fuel cell, can operate with these types of fuels as well, besides gaseous hydrogen. So we believe that for different applications, different options could be used.
Yeah, in particular, the things like methanol, you don't need to clean it up excessively. You could probably do an onboard reforming and use it fairly dirty, which is an advantage of the high temp pen membrane.
I think the discussion is going to go back to Rory's basics. The discussion is going to end up being what kind of predictive technologies do you have built into your fuel cell system so that when you're in flight, you have the ability to understand when failure of something is about to happen before it causes something consequential to the ability to power the aircraft. I think that's the question that's being asked. And so it goes to what kind of cell testing have you done thus far? What kind of individual cell predictive monitoring will you have on the stack? What kind of ramp rates do you have with your turbine compressor in the middle of it so that it doesn't have a failure? Can it handle moisture on it? Can it handle ice crystals? All of those kinds of things are elements. It's not so much the hydrogen part of it, but when you're building your complete system and you're going to put it to the FAA for certification, you need to be able to have some predictive history and documentable characteristics to bring to the FAA through the partner you're working with.
Yeah,
We've started a lot of this, looking at power ramp rates, shutdown startups, cold, hot, wet, dry operation, as you said, is to look at the variations in climate and weather that you might experience. So a lot of that has already been started, particularly even with the prototype, the short stack that I showed today. And it's to develop that database so we could have the predictive power.
Very good.
I have a question on a different part of the subject, if you have a moment. It's turbo air cooled. so that you can operate at the higher temperatures. My question is on pre-start and post-shutdown, when you're, if as shown in your diagram here, you're getting air off the motor that's compressing the air. How long can you operate without that? I.e., when you're starting up and you don't necessarily have a lot of airflow, or after you're shut down and you're hot and you no longer have the airflow of being in flight, what are the issues there?
Yeah, well, actually, the previous history in high temp PEM has been without the turbocharged pressure. And so there we have an awful lot of data that says if the pressure is not there, it still operates fine. Not as high a power, but it operates fine. There's no, we've done tens of thousands of hours under those conditions. So that doesn't present much of a problem if the pressure is not there.
Okay, no damage to the to the motor or to the fuel cell when it needs to operate again.
No, you would if you had the pressure off, you would simply turn the turbocharger back on, bring the pressure up, and then start operation at the higher powers.
Okay, thanks.
Thanks. I have a question from Rick Kotze for you, Brian, or perhaps anyone else. Does anybody have an informed opinion on H2 Pro's ETAC technology that recently received investment from Bill Gates' Breakthrough Energy Ventures? Anybody?
I don't have any inside information on that.
Okay.
I don't know if anybody else does, but I'd like to hear it too.
Yeah.
Sounds like an invitation
Bruce.
opportunity.
Yes.
Yeah, Bruce, do you have any further thoughts?
No, I was just going to say I do not, but I just suggest maybe there's an opportunity for an invitation to the
Yeah. Okay.
schools there.
Yeah, we're making note. We're making note. We'll reach out. Very, very good.
I've got a question.
I have a bit of an off diagonal question. There was an article recently in The Economist titled under clean energy, titled "Toothpaste in Your Tank." It was about a magnesium hydride storage means for hydrogen hydrogen carrier paste, basically, with a water-based release mechanism. Do we have anybody here who has any insight into this? This work came out of the Fraunhofer Institute for Manufacturing Technology and Advanced Materials in Dresden. I'm just curious if there's any knowledge around the horn here about where that technology is, and I know it's pretty low TRL at this point, but whether it matters in our schemes of things.
Well, the storage for hydride, metal hydrides in general, a lot of people have been working on. The Department of Energy had a big program and created some super centers to try to look at that. You can't store a lot of hydrogen for the weight that's there. And so that's where people are trying to improve that. I'm not sure I have the exact most recent work on how high they can push that limit. My last understanding was it'd still be a little bit heavy and low hydrogen content for what we need in aviation. But they were hoping to do it more for what I'll just call the terrestrial transportation, for potentially for cars, so that they could get away from a high pressure tank in a car.
The article, well, keep in mind it's The Economist, not one of our technical journals. More energy per liter and per kilogram than either batteries or petroleum can manage. It just sounds like an interesting, like I said, a little bit off diagonal.
Mm-hmm.
Can you guys hear me?
Yes.
Yeah.
I can hear you. You're faint though.
Let me turn my mic up. That'll be an interesting. You won't want to miss next month's council meeting. we'll have HyMark, which HYMARC. It's a group of 5 national labs where they are investing and doing tons of research on that very topic. They'll talk about the TRL level of hydrides and their uses. So, and they'll be able to go over that in detail. Brian, I had a question, and I apologize, I dropped off for a second. So if this has already been asked, forgive me. I was wondering if you could talk to the life cycle of high temperature systems compared to a low temp system.
Yeah, so we do have some information. The high temp system is actually pretty robust. We've operated continuously out to 20,000 hours. We've done lots of start-stop cycles. We've done load cycling. We've tried to mimic an awful lot of duty cycles of, non-aviation applications, and the general feedback is it's pretty robust. We know something about how it operates under these. We know how to manage that. Some of this is just managing, so you tell the device not to go outside of a certain range. It's not limiting in the sense that that it stops it from being used in the applications. It just, when you're in that application, make sure you do the smart things with it, right? And so that's always a nice solution, because it's essentially a computer program that says operate here, but don't go over there, right? That's a cheap fix. It's a computer program, and so we like those kinds of solutions. But you do have to know, what happens during load cycling and start stops and all the rest of it, temperature variations, in order to then define the window. But we have a pretty good window, and I don't see anything in aviation that's outside of a lot of the window we've already been operating in.
Hey, Brian, this is Rich. Could you just comment to the audience about the consistency of performance for the high temperature membrane up to higher altitudes, like up to and above 20,000 feet, for example? And also your ideas about, the water vapor that's produced and how we should deal with that, if anything. Thanks.
Yeah, now the system, on both sides of it, will be pressurized on both the hydrogen and the air side. And so, regardless of the changes in atmospheric pressure, we will be controlling the pressure internally of the system. We've started to do some testing to now understand a little bit about altitude, because that's a new factor. Keep it internally pressurized. We've done some extreme temperature testing. I think I mentioned it a little earlier, of very, very cold areas, external environment, hot as high as 35, 40 degrees C. So that's about as hot as I think we're going to get. We've run it really dry. We've pumped water into it just to see what would happen if we were in humid systems that were also very hot, for instance. And so we've done a lot of this on our short stack prototype, in fact. And we're happy with what we've seen so far.
Brian, may I add a comment? Sorry for this. Thank you, Rich, for a very interesting question. We are in communication with a number of potential clients that are going to building systems for very high altitudes. And we did some analytical work for them. And we found that high temperatures, high operational temperatures of our system allow us to provide us a lot of opportunity to compress air multiple times without essential spend of energy, because this allows to recover essential part of energy spent for compression using high temperature from our side, from generation side, and using low temperature of outside air. Just an idea. We use turbo expander on board for this. Thank you.
And my last question is about the water vapor. Do you have any thoughts on that for the audience?
We've looked at a lot of different conditions for the water vapor. Particularly compared to the low temp PEM systems, they are very sensitive to being highly humidified and not going too far away from those conditions. We've done bone dry and extremely wet. We like to think of the high temp PEM as being climate independent. So whether you're high relative humidity or low, doesn't make too much of a difference, frankly. So that maybe is actually a benefit when we compare to some of the low temp PEM systems.
Thank you.
Brian, Rory again.
Yes.
If I remember correctly, when you were talking about the variety or maybe the different types of hydrogen fuels you could put in there, if you were to think of it from a logistics and infrastructure perspective, what do you think is the best supported fuel type of hydrogen from that perspective, and how well, I'll use the word tolerated, maybe that's not the correct word, but how is the performance of the system using the best supported hydrogen fuel source from an infrastructure perspective? Over.
Well, from an infrastructure perspective, a lot of people are working on making hydrogen available in lots of different environments, right? For not only for cars, but potentially for air transportation. And those thoughts are still ongoing. If you could, then that would be great, because it's the most purest form of your fuel, and you don't have to worry about any dilution effects, or you have it pure on site. Then this is probably the best for the operation. If other considerations come in and people say, well, we really want to go back to a liquid-based fuel in a plastic storage tank and not have a pressurized, say, hydrogen system, then we can make that work too. This is being done already. It's not quite as pure in a fuel, so you might see a little bit of dilution effects. Maybe we have to figure out how to go even more concentrated in the hydrogen than what's produced easily right now from something like methanol. But some of this may be not necessarily our call, but we could work with either one.
Are there any specific safety concerns maybe that the infrastructure side would choose without necessarily prioritizing engine performance?
California is probably the leader, and there's a lot of talk about putting in hydrogen filling stations already. And if that goes forward, we're going to learn a lot from California's early installations and making sure that's safe. The people, if you read through the automotive literature, the people at Toyota have been working for actually quite a few years in developing, the hydrogen filling station model. Honda has been heavily involved in what that filling station would look like with a number of other industrial gas partners. There's actually some joint development work, I think, with Plug Power on a filling station. So a lot of the industry is involved with understanding what we would need for a safe and easily implementable filling station module. So I actually think that's going to happen. I could be wrong, but I think that could happen. And, for aviation, we'll simply build off of their learnings and port that over to our own filling stations.
Brian, Thomas.
Thank you very much.
Thomas Jones here from Plug Power. I enjoyed your presentation. Thanks very much. And very interested to see the advancements in high temperature membranes, because it's certainly been the holy grail of fuel cells ever since, the automotive OEMs were complaining about the sizes of the radiators in the mid-90s of trying to get them into the vehicles. I have a question, namely to do with overall system level efficiency. And you have a couple things, against you. One of them is that you're compressing both your reactant air and your cooling air. And as you go to altitude, as you know, that's going to be a relatively big hit from a compression perspective, from a pressure ratio point of view. The other thing you mentioned is lower cell efficiency. And with that comes the need to carry more hydrogen. So if you're, you may have a high specific power of the stack, But when you look at it at an overall system level, you may need to obviously carry twice the amount of hydrogen to have the same range. So could you comment about those two things?
I'll start with the hydrogen one, the last one you just said. I don't think we'll waste very much. You can imagine operating under a dead end anode architecture, so you're actually not wasting any of the hydrogen. It's not like you're going to pass it through and then operate under efficiencies where you're going to throw away 20% of it or something.
No, but you had indicated that your cell efficiency is 50% of, say, the low temperature membrane.
Well, what I was thinking is that not so much the cell efficiency as where I think we can go to. I mean, we're at 2 kilowatts per kilogram now. And so if our goal is 4, we're halfway there. And so it's not quite the same efficiency. I'm thinking of what we need for air transportation. And I think we can massage out even more than what we've got now at 2 kilowatts. If you hit 4 kilowatts, which would be the 50% of a rough calculation, then I think we've got a system that'll satisfy a broad range of aviation applications. That's what the 50% came from.
Right.
May I add a comment? Sorry, again, Brian. First of all, I would like to emphasize that we are talking about specific power for the system level, not for a stack. The first. The second, when we are talking about efficiency, we should separate efficiency at peak off mode in hover mode and efficiency increase mode. So the main hydrogens we spend during cruise mode, and in cruise mode, our system operates at essentially higher efficiency in comparison with when it operates in peak mode. You see, our system operates without buffer battery. So HTPM fuel system covers all peak shades by itself, and efficiency varies in wide range depending on operational mode. So average efficiency of our system not lower than for LTPM, because we recover essential part, again, we recover essential part of energy spent for compression. High operational temperature allow us to use a turbo expander and recover up to 80% of power spent for air compression.
Interesting.
These allow us to reduce essentially hydrogen consumption and increase efficiency.
So let me make a quick comment and a small question. If you can get 4 kilowatts per kg, people will throw away turboshaft engines. So you don't need to be there. Even 2 kilowatts per kg is a dream target. So a quick question I had for Brian. So should we use the lower heating value then for high temperature PEMs? And if so, is that an advantage even for cooling? Because that's a big deal for VTOL.
So I'm not sure.
So when you calculate efficiency, is it 120 megajoules per kg we should use now because we're not using the latent heat of vaporization?
Well, let's see. So yeah, maybe that 50% I threw out was a bad number because I was using it not so much the efficiency of the stack as, basically how much more I think we have to go from our current 2 kilowatts per kilogram to potentially a 4.
Yeah, this is a separate question. I'm just curious.
By the way, I got started on the efficiency. Sergey, maybe from an engineering perspective, what is our models using now?
Models of what? Sorry. I didn't catch, actually. Sorry for this.
So when we calculate efficiency, we usually use the higher heating value. But now with high temperature, since you're dealing with vapor, should we now calculate the lower heating value to calculate efficiency? The cell voltage divided by what? Is it 1.42 volts? Or?
Yeah, it's clear. Thank you. So sorry. Typically, for all fuel cell systems, including traditional LTPM systems for transportation, a low heating value is used. And when we are talking about fuel cell efficiency, we always talk using low heat value because water actually produced in vapor form in all fuel cells. Is this answer for your question or not?
Yes, yes. Thank you.
Sort of off topic, but since I didn't hear anybody else asking questions, if you still have a question, you can still ask it. But when we were talking about refueling stations, at one point we talked about getting a map of existing pipelines. And if such a map exists, I think it would be really valuable to include that in our roadmap or our blueprint, whatever we're calling it. So if anybody knows of something like that, we would love to see a copy of it.
Danielle, this is Charlie. I'll come back with you offline. And for those that are on the call, there are hydrogen pipelines on the Gulf Coast, essentially from New Orleans over to the Houston marketplace. There are no hydrogen pipelines in the Northeast that I'm aware of at the present time. And the only pipelines on the West Coast are basically in the greater Los Angeles area around the refineries in Torrance. Otherwise, you're not going to find them in the US for your roadmaps.
Okay, thanks.
Since you were off, you started by saying it's a little off topic. I'm glad you started that way. So let me stay off topic. So there are some technologies where you could put hydrogen into natural gas pipelines and still maintain that hydrogen content below the hydrogen embrittlement points, and then very efficiently pull that back out using the high pressure natural gas lines, because there's already hydrogen and a lot of natural gas anyway. It's very off topic, but it's a separate technology, but a little bit related to the whole, hydrogen fuel cells and kind of that structure and architecture. So there's ways to do it. People haven't taken advantage of it yet, but I think it's quite possible. And that would make the hydrogen distribution an awful lot easier.
The issue has been the associated emissions with reformation technologies to pull the hydrogen back out of the natural gas. And thus far, the industry really hasn't seen a good membrane technology that's not reformer associated with zero emissions on it. So natural gas pipelines are great to add hydrogen to supplement them, but they're not so good to try and pull the hydrogen back out of again. If you want to abandon the natural gas line and use it solely for hydrogen, that's one thing too.
Yeah, I think there is some technology available, but people haven't taken advantage of it yet.
So Brian and Charlie, who is or who are the leaders working on that particular problem or challenge? Are there private sector as well as government entities?
I don't know about the government. There was some private sector work. I'd have to look back into it to see if who's pursuing it now. I could certainly have that discussion with you a little bit offline later. We could dive into some details.
Thanks.
Yeah.
No.
Bud, go ahead, Bud.
Yeah, sorry, the daylight savings time change screwed me up, so I'm late. I wanted to be here earlier. Three things. One, to Brian, I know a little bit about Sol-Gel. I was in central research for 10 years, and their MRIs or whatever you call the devices, and his Sol-Gel method for making the membrane is brilliant, pure brilliant. And I'm speaking to anybody who is interested in investing in this company or working with them. This is a breakthrough technology. The way they're using it is breakthrough. It's just fabulous. The most important
Can you put a link to that company in the chat room, please?
No. You don't link to 3M. And that's 50 years ago. So, I mean, 50 years worth of research that they've been doing, and generally this stuff. But more important is that the most important use of hydrogen is for a vertical takeoff. It's not to power these aircraft that are going to fly from here to Beijing and back and borrow money. The most important is for vertical takeoff. And so therefore, a fairly large truck-sized vertical takeoff aircraft should be carrying around hydrogen. So instead of having trucks and pipelines and all this stuff that I just heard, you really use a flying gas tank, or you got a vehicle, a Chinook type vehicle that picks up large tanks of liquid hydrogen and carries it. And the reason is liquid hydrogen has to move quickly to its use. So the best way to move it quickly from some solar cell array or windmill to a point of use would be us, meaning we are the solution to bring hydrogen to everybody else. And the most important thing is an advice to Brian and his buddies. You really have to focus, please, I beg you to focus on using liquid hydrogen in your first successful la-di-da versus versus pressure tanks, because liquid hydrogen is a lovely thing in a vertical takeoff aircraft as a cooling medium. So you can actually cool the fuel cell, you can cool the storage tanks, all kinds of stuff if you got to go to liquid hydrogen temperatures. So the breakthrough would be fueling your fuel cell with liquid hydrogen, and there are lots of little ones that are as powerful as you know how to make, because you might have 2 or 3 or 4 places that you're going to have a motor, and that motor right behind it has a fuel cell, that fuel cell is being fed by liquid hydrogen. So that's my contribution. I'm sorry I'm late. I hope you heard something.
Thank you, bud.
Yeah.
I'm just kind of catching up on the chat. So at HyPoint, Brian, you guys are not using batteries at all, or you are combining this system with batteries? I'm a little confused.
No, we would not. We're not going to typically put batteries in unless somebody else wants it.
You can get enough power for the hover operations. You might have said that again. I cut out, so I missed some of it.
Yeah, we can. I mean, if somebody wants a battery in there, it depends upon the design. You know, we can do that, or capacitors, ultracapacitors, but typically we're going to try to develop this to be a fuel cell only system.
Mm-hmm. And what's the specific power that you're shooting for?
Well, so let's see if I can back up. So what we've got is in this. Let's see if yeah. So right now we've hit 2 kilowatts per kilogram in our prototype short stack that we just announced and the results of in December. And so, and that will translate up to larger systems, which is what we're going to do over the next year or two. So that puts us into a market for a lot of things already.
Is that including balance of plant?
This is the system. That's right. This is the system calculation. And again, you know, you said you kind of tuned out a couple of times, you dropped, but so one of the things that we're doing is using the turbo charger to provide pressurized air as well as the function as the cooling system. And so what we've been able to do is get rid of a lot of weight because we don't need a liquid cooling system as part of our balance of plant. And that saves a tremendous amount of weight.
Colleagues, sorry, may I add a comment to the previous question regarding liquid hydrogen, if it's important. You see, I missed this question because I was answering to the chat. We studied the question of using a liquid hydrogen for cooling the system. This is very interesting, and we found that we would able to drop, we and other fuel cell developers would able to drop up to maximum 8% of heat, produced heat, to liquid hydrogen, because actually fuel cell consumes so small amount of hydrogen. So even hydrogen, even liquefied and cooled up to 6 degrees Kelvin degrees, does not allow to drop a lot of heat. We are going to use liquid hydrogen in order to increase efficiency of compression. It would be much more efficient way of using this this energy spent for liquefying of hydrogen, rather than heat rejection for cooling to cool fuel cell.
Sergey, may I speak? Bud Scriba? May I speak?
Hi. Sorry, it's difficult to...
Go ahead, Bud.
Mhm.
Go ahead.
The big deal for liquid hydrogen is that's the way you push around energy from a vehicle. If you are all within the Stanford Research Institute world of study, you know that liquid hydrogen or hydrogen can be very cold, and very cold could also cool down superconducting electric motors. So a smaller superconducting electric motor is kept cold. The fuel tank is kept cold. The lines of carting energy from one part of the building, one part of the aircraft to another is not by electricity. You are brilliant in putting your fuel cell right behind the electric motor. That's your designs are beautiful. Everything I've seen you do is worth investment. But the trick is, in the future, if in fact we're going to have a hydrogen economy, the idea of us being the bucket to carry hydrogen from one place to the other. We're the bucket, we're the truck. If in fact we can haul around hydrogen in our aircraft, we can haul around in an external tank by all those guys who are trying to do hydrogen storage tanks. The trick is it's cold. So the aircraft should be designed from scratch on a white piece of paper that it's going to be cryogenically centered for the motor, for the tank, for the fuel cell, all that kind of stuff. It's not just for cooling the fuel cell. And I didn't mean to say it. If I said it, I didn't mean it that way. It's a systematic breakthrough. And the point is that because of who you are, you could actually do something with liquid hydrogen on something less than a megawatt type of engine that you would normally use for bigger airplanes.
Yeah, thank you, Bud. Thank you for the comment. I agree. There are a lot of space for optimization with liquid hydrogen for increasing efficiency and additional weight reduction. The main achievement with liquid hydrogen is lightening of fuel tanks. At the moment, as you know, 30% of mass factor could be up to 30% for liquid hydrogen. In comparison with compressed hydrogen, it's just 10%. So we understand that liquid hydrogen could provide a lot of benefits for fuel cell powertrain as a whole, including motors, fuel tanks, all components, compression system. Yes, this is our future, but we are ready to provide a reliable system, very high efficient system at the moment, in a couple of years, at maximum.
Get all the money you can for that, but I'll be right behind you 3 years later, applauding your conversion to hydrogen. And also, just anybody who's listening to this, who's either an investor or wants to buy something from you guys, I am really impressed that they actually, I've been caring about this fuel cell thing for 20 years. And the assumption is that nobody knew how to do it right on tanking and or fuel cell. You don't take a fuel cell from a Mirai from Toyota and try to stick one that was well designed for a car into an airplane. And you guys figured that out a long time ago. So the whole thing is everything has to be light. But more important, the advantage of liquid hydrogen, I was against liquid hydrogen. I'm in favor of a thing that I helped invent. It's called the cryogenic flux capacitor with NASA. which is a storage of hydrogen under pressure on an absorber material in a cold tank, meaning at 77 Kelvin, you can have a very cold tank under pressure, 2 to 3,000 PSI with an absorber material, and you get a very, very good tanking scheme. And I helped design that, and you know, they call it a cryogenic flux capacitor. And I didn't like cooling hydrogen down to liquid because of all the energy that it takes to come to liquid, and it takes energy to get it back out of this stuff. So I was against liquid hydrogen until you guys said you could use it in a fuel cell architecture. And I said, okay, these guys are smarter than I am by a mile. So I will support anything you do, including trying to stuff this into something that the Airbus wants to take off and fly around. You know, we don't need more competition with the 737 MAX because that is now going to be considered the safest, cheapest airplane for the next 20 years. And trying to replace it with a hydrogen, expensive, difficult to fuel, difficult to sit in aircraft with hydrogen. It's the wrong market. It's a marketing statement I'm making. There is no market for hydrogen fueled aircraft except for the monies that you can get from the government, from the United States and Europe to build, or China, to build something with a hydrogen in it. Let's use the hydrogen on the ground like the Japanese do in a fuel cell that heats the house. So you make your electricity, you make your heat, and you put that in a little house, and you pipe new types of pipes to the house, you know, on the ground. But the key issues for liquid hydrogen, you got to get it there fast and use it soon. And therefore, we can fly, you know, 1,000 pounds of hydrogen in a tank that we just drop off and go back and get another tank and take back the empty tanks. So we are the UPS or U-Haul mechanism for the true use of hydrogen. Even though it's a pain in the ass to cool it down to cryogenic, to liquid temperatures. And to cool it down, you don't use the way we use it right now. We've got to have a much smarter way of cooling it. So if you understand what a fuel cell is, figure out, take your fuel cell membrane technology and make an electrolyzer. Take air and electricity and make hydrogen. So there's a breakthrough also needed on the electrolyzer side, which may or may not come from the PBI membrane scheme. I think an electrolyzer that is a reverse engineered fuel cell, which you guys can do in your sleep, is the end all. And
thanks for the comment.
Yeah.
I'm trying to help. I'm 78 years old, be dead tomorrow. Couldn't even wake up in time to get this thing at the right time. So I apologize for being late and shooting my mouth off so badly.
Apology accepted.
So, my phone
we do R&D in this direction as well. But thank you for your
faster than these guys.
comment.
I will give you $10 billion if you call me one day.
So let's be mindful of the time and try to remain agnostic in terms of, you know, who our personal favorites are. We really want to provide everybody with an equal opportunity to, you know, present their solutions. That said, it could be an interesting topic for a future presentation on hydrogen supply chain. I don't think we have that. And this is probably a good time to transition to sharing my screen. So if Brian, if you could stop sharing and I could share my screen, I'll show you guys our tentative schedule.
I'm trying. Hang on a second.
Yeah, no rush. We've still got 15 minutes, so.
Let's see. There you go.
Thanks. All right. Can you see this yellow highlighted of Brian? All right, so here's where we are. So like I said, next month will be HyMark. I'm really excited about that. That'll be focused on very interesting onboard hydrogen storage, from, you know, everything from the toothpaste looking stuff to pellets and everything in between. So that'll be next month. And then after that, in May, we'll have intelligent energy. And then we're looking at for June, hopefully hydrogen forward, pending that that contact coming through. And then July, I can't remember what BC stood for, but Mike Diamond, you probably remember better than I do.
Yeah, that's British Columbia, and the province is gearing up for the export of hydrogen, initially targeting the California marketplace.
Okay, perfect. And so those last two are tentative. So these dates down here are open. I could see hydrogen supply chain being a really good one. If anybody has any suggestions for future topics that we haven't yet covered, now is the chance to get those on our radar.
So Danielle, this is Richard. I've been reaching out to Michael Romanowski at the FAA, who's in charge of Air 600 innovation and fuel cells and if you will, and I'm clearly not well spoken enough because he's not replying. So I wondered whether someone as influential, obviously, as yourself or the two Michaels could reach out to Michael Romanowski if you know him. I do know him, but he's just not replying, and I don't want to become a bad smell to him, but I have tried.
Yeah, I could do that.
Oh, great, Michael. You know,
yeah.
there are a lot of Michaels around.
We know each other.
Oh, perfect.
Part of the Mike's Club.
Yes, clearly.
I don't know if I butchered the spelling of his name, but
as in Roman, and then I think it's OWSKI, Romanowski.
Okay, spell check for the win.
Yeah, and I think he's director of Air 600, if my memory serves me correctly.
Yeah,
that's correct. Yeah.
I do want to just mention that we didn't update the times here,
good point.
Yeah, and it's also not. It's also didn't recognize a change to daylight saving time and standard time. But anyway,
yeah,
it's this time.
Yep.
I'm sorry, Danielle. Rory, just real quickly there on that last point to Mr. Romanowski. Any other potential points of contact in the FAA you think we should be reaching out to? I do know one person on the vehicle certification side as they go through their, basis for certification, which the FAA is currently doing, and this will obviously be a part of it. I just don't know if that's the right place to start. Over.
So is there any certification activity underway in hydrogen right now at FAA? Do we know? Does anybody know that?
I don't know that, so that's not what I'm saying, just to be clear, but they are on the vehicle side, of which I would think obviously the hydrogen piece will be part of that, and that's why I was suggesting maybe somebody on the vehicle side. Over.
Yeah, very good. So Michael Romanowski is probably the guy in the know, Rory, about what's going on, if anything, in hydrogen, since he's AIR 600.
Yeah.
Why don't we check with him?
Yeah, I completely agree. I've had conversations with people, as Rory's been alluding to, and I think Michael will be able to give the gouge on what you're asking, Rory, across the piece, actually, in terms of means of compliance. In my conversations with the FAA on this particular topic, it's so cutting edge. We're like we really are onto something, and they're still trying to deal with it. That's all I can really say right now. But Michael, I think, would be the good man.
Yeah, the last I heard from FAA on hydrogen, it was their concern about the Hindenburg. So they have a lot of catching up to do.
Yeah, they do.
Yeah. Well, to some of my earlier comments about, hey, don't want people to default to the old way. So how do you help steer towards a new, open way, if you will? Over.
Yeah.
I think when you reach out, Michael, to Romanowski, I know him as well. Feel free to add my name to your group, asking him, to consider a briefing on the topic and include the idea that he might want to draw on the subject matter expertise from the tech center, from Michael Waltz. Who is a principal there, working through quite a few of the projects that the FAA currently has active in hydrogen, which I think we all will benefit from hearing about. And
how do you spell Michael Walsh's last name?
I like the dance, W-A-L-Z.
Thank you.
Yeah, and I think, you know, there will be sometime in the next, I don't know how many months, in the Federal Register, there will be published the G1 Stage 4 certification cert basis documents from companies that, you know, will be finalizing their terms, both the rules and means of compliance for hydrogen.
Very good.
Michael should be able to talk some about that pretty soon.
And Michael, one other thought, we could reach out to SAE. So the two committees, we've got to get this right, EA7A, which I think is hydrogen fuel cells. Someone correct me if I'm wrong. And the other one is E40. Those are two possibilities. I was just thinking about standards on this particular topic. And I do know that ASTM have got a committee on fuel cell technologies as well under F38 in the UAS kind of eVTOL, because the eVTOL is crossing boundaries between F38, F39, F44, etc., as I'm sure you're aware.
Great. So, Rich, why don't we do a follow-up call maybe later today, and I can take better notes from you.
Yeah, no, absolutely. Delighted, Michael. Just give me a ring. Sure. What time? After 3 o'clock will be great. 3 to 4. How's that?
And we're probably at the time or the point where we want to start getting some more of the different associations and organizations like Gamma and the other organizations involved in this initiative.
Good point, Michael.
Hey folks, this is Carlos from Embraer here. I'm currently the secretary of the SAE group of Fuel Cell. So I believe the chairman, Olivier Savant from Dassault, would be happy to provide a presentation when I believe in one of those dates that Danielle wrote. And on the F-38 as well, I'm also a member of the F-38. There is a standard that's being published. I'm not sure if it's already published or not, but was being written by Phil Robinson from former Ballard, now Honeywell. I was involved in the ballots cycle, but it's a pretty good standard that could be also used.
Yeah, I think, Carlos, that was due to go out for ballot, was it not? Phil Cannell called me the other day because been difficulty finding Phil up at Honeywell. He was sort of MIA, but he's now back online. So I'm not sure whether that ballot's going to come soon. Don't know.
We've also reached out to Buzz McCain with Ballard. Does anybody know Buzz? I think he's on the old side of Ballard. He's not on the side that Honeywell acquired. But having somebody who's in the Honeywell nest right now would be useful.
I believe we do. I think his name is Jia. I'm not sure if I'm saying it right. If he's on the call, please speak up.
Yeah, Jia Ju.
Yeah, he might not be here today.
Yeah, I got a name from that was replacing like Phil Robinson and the SAE group that I can forward to you.
Fantastic.
And yeah, I can vouch for Carlos's group is doing some really good work. I was supposed to be part of it still. Thank you for joining ours, Carlos, and I would like to eventually join yours again. Things have been busy, but they've got a very good working document going. So I think that would be excellent to have you guys be part of the standards meeting.
Sure. Yep. We've done a presentation in the F44, ASTM F44 last week, and I believe we're trying to, and also in the SAE electric steering group. So the hydrogen is really getting body all over the agencies.
Good. All right.
So Danielle, we're sort of at the end. Maybe we
Yep.
should wrap things up.
Yep. That's really it. So yeah, thanks everybody for coming. And thanks again, Brian, for that excellent presentation. And this is recorded, so I'll send out an email where you guys can access the recording. And if you haven't already joined Vertical Flight Society, please do so. And with that, everybody have an excellent week.